The decision to salvage the Imperial German battlecruiser SMS Seydlitz meant stepping into a highly volatile industrial arena. Pneumatic buoyancy would be the lever, and it was never gentle. Pressurizing wrecked compartments could overload the ship's internal structure and force failures where the steel was weakest. Even when the hull held, the job became a grinding series of major lift cycles before the wreck could finally be torn free of the seabed. The kill was entirely self-inflicted and aggressively executed. On June 21, 1919, the massive German high seas fleet lay interned at Scapa Flow. Under sweeping orders to prevent the fleet from falling into British hands, the crew of the Seydlitz initiated a deliberate scuttling sequence. Valves were thrown wide, water flooded the lower spaces. The ship was a 25,000-ton fortress of heavy steel armor, massive naval weaponry, and immense displacement. The internal labyrinth of the Seydlitz was heavily subdivided into countless watertight compartments, originally designed to keep her afloat under heavy enemy fire. By intentionally breaching those deep internal defenses from within, the crew turned the ship into a massive, uncontrollable sinking weight. Once the internal equilibrium was deliberately broken, gravity took absolute control. The enormous battlecruiser began her final descent. But the sea floor in this specific anchorage was relatively shallow. The Seydlitz did not vanish into an abyss. As her lower decks filled, she rolled heavily onto her starboard side and struck bottom, ours driving deep into the mud and locking herself under dense sediment and crushing pressure. Yet a vast section of her upper hull remained visible above the surface for years. Contemporary observers described the exposed armor as a small, dark island in the bay, and small craft navigated carefully around its immense curve. It loomed on the horizon as a monument to the self-destruction of an entire fleet. This deceptive resting state created a unique industrial temptation for heavy salvage operators. Steel breaking the waves can look like easy access, but in extreme marine salvage, that surface visibility is often a trap. The exposed flank is only a fraction of the problem. To the untrained eye, the ship seemed to be resting in the shallows. The real fight was buried below the waterline. His experienced marine salvage engineers looked past the surface. They understood that the protruding steel represented only a tiny fraction of the overall mechanical problem. Below the waterline lay the flooded warship, heavily embedded in dense suction mud. In the 1920s, there was no practical machine that could simply hook onto an entirely flooded battlecruiser and haul it cleanly upward through the water column. The environment around the sunken hull was unforgiving. The steel was thick, built to withstand the heaviest naval artillery, and now it formed a rigid, uncooperative barrier against any external extraction effort. To claim the metal, engineers had to confront the raw physics of dead weight, internal water volume, and unrelenting seabed suction. Every single compartment, corridor, and bunker below the surface was holding thousands of tons of seawater. The mud gripping the starboard side acted as an enormous hydraulic clamp, anchoring the massive steel structure rigidly to the earth. Breaking that subterranean grip would require immense, sustained industrial violence. The salvage operators looking out at that exposed flank understood that they were not merely recovering high-grade scrap metal. They were preparing to fight the entire ocean for possession of the hull. What mattered was not what showed above the waves, but the physics below. The geometry of the sunken battlecruiser created a physical trap for any conventional recovery. A warship resting on its side with one flank exposed presents a massive flooded volume open to the sea. You cannot simply drop suction hoses into the dark and attempt to pump the water out. The surrounding ocean is infinite. As fast as surface pumps can remove the dead water, the immense surrounding hydrostatic pressure will force the sea right back through every shattered pipe, torn armored plate, and open hatch. The geometry dictates that trying to empty a sunken steel box from the top down is a completely losing game. To generate upward lift against thousands of tons of dead weight, the salvage engineers had to reverse the physics of the sinking. They decided to manipulate displacement from the inside out. This is the brutal science of pneumatic buoyancy. Instead of pulling the immense weight of the ship upward with external cranes, the engineers would force the ocean outward from the inside, as they would turn the flooded iron corpse into a massive pressurized diving bell. The engineering decision was methodical and highly dangerous. The team had to establish an airtight envelope, working from the exposed surface downward toward the dark waterline. Because the port side of the battlecruiser protruded above the waves, the salvage crews possessed a solid staging area to begin this intense physical labor. Men crawled across the slick, exposed armor plating. They carried heavy steel patches, welding gear, and thick timber planks. They systematically hunted down major openings and obvious leak paths in the steel skin. Air trunks, ventilation routes, access ways, and damaged fittings had to be blinded and sealed wherever the structure would allow it. They bolted plates over gaps and used cement and timber packing to build rigid, unyielding closures. The objective was to trap a pocket of gas inside a ruined steel labyrinth. Once the upper sections were sealed tight, heavy industrial air hoses were dragged across the wet steel and bolted securely into the hull. On the surface, massive steam-powered compressors ignited. They began driving high-pressure air down into the flooded compartments of the dead warship. The physics involved are counterintuitive but relentless. Compressed air behaves like an invisible piston. Fed from above, it expands through sealed spaces and forces seawater out through whatever submerged openings still remain below the waterline. By replacing heavy internal water with trapped air, the salvage crews were manufacturing artificial upward displacement. They were building lift from within. This aggressive method introduced a terrifying local constraint. Pumping immense pneumatic pressure into aging steel drastically alters the structural loading of the ship. A battlecruiser is engineered to withstand explosive impacts on its exterior armor. Its internal bulkheads are designed to resist the inward crush of flooding water. The entire internal architecture is built to push back against the ocean. It was never designed to hold extreme high-pressure gas expanding outward. By injecting compressed air into the lower decks, the salvage team subjected the internal walls to unnatural, extreme outward stress. Every steel rivet and heavy iron plate groaned under the severe pneumatic load. The high-pressure air constantly hunted for the weakest point in the boundary, threatening to blow the internal walls apart. The topside machinery hammered away without pause. The steam compressors roared, steadily feeding the massive invisible air bubble trapped inside the hull. The engineering logic of this pneumatic lift was sound. The internal displacement slowly began to fight the immense suction of the mud, but maintaining this extreme artificial pressure required an enormous array of heavy topside steam engines operating continuously. Those engines demanded an uninterrupted, massive supply of external fuel to keep the fires burning and the compressors firing. And that critical external fuel supply was about to completely vanish. In the spring of 1926, the narrow window for continuous salvage operations suddenly slammed shut as a national industrial strike disrupted coal supply and sent the entire fuel chain into chaos. The steady flow of coal that kept remote steam machinery alive became uncertain overnight. Out on the salvage site, the steam-powered compressors could not be allowed to go cold for long. If the fires died, the compressors would stall, the surrounding ocean would push back in, and the fragile buoyancy inside the hull could be lost. The salvage engineers were isolated, completely cut off from the mainland supply chain, and forced into a radical logistical decision. They realized that the dead warship beneath them contained exactly what they needed to survive the crisis. When the massive battlecruiser was originally sent to the ocean floor, her deep internal fuel bunkers were fully loaded. Trapped beneath the cold water and heavy armor plating lay an enormous stockpile of high-grade Imperial naval coal. The engineering team decided to execute an improvised in-situ resource extraction. They would physically mine the flooded wreckage to fuel the very surface machines trying to rip it from the mud. This was raw combat engineering applied to heavy maritime salvage. The team shifted their immediate focus from lifting the vessel to breaching the wreck where it was accessible. They cut into the exposed hull to reach the coal bunkers that still held usable fuel. Then came the grinding work of extraction, wet coal dragged out by hand and with simple grabs and hoists, hauled up onto makeshift platforms and stacked where the boilers could reach it. It was exhausting, brutal labor, pulling dense, dead weight out of a dead ship just to keep the salvage plant alive. The dripping wet coal was fed into the fireboxes of the topside steam plant as fast as the crews could deliver it. It burned dirty and hard, fighting its own waterlogged weight, but it was enough to keep boiler pressure up and the compressors running. Heavy black smoke poured from makeshift exhaust pipes mounted on the ruined hull. The massive surface pumps roared back to life with renewed fury. The entire salvage site was now operating on a brutal closed loop. The topside machinery was breathing pressure downward, fueled by coal pulled from the battlecruiser's own bunkers. The sunken warship was physically powering its own mechanical extraction. The relentless manual extraction of submerged coal kept the heavy surface fires burning day and night through the duration of the national strike. The immense steam pumps never stopped hammering on the exposed steel flanks. They continuously forced massive volumes of high-pressure gas deep into the dark lower decks of the heavy hull. But solving the immediate surface fuel crisis only accelerated a much more dangerous physical problem developing deep inside the sunken wreck. The constant, brutal injection of forced air was heavily stressing the aging iron walls below the waterline. The rigid internal architecture of the battlecruiser was quietly stretching toward an absolute structural breaking point. Deep inside the buried steel labyrinth, the continuous injection of high-pressure air kept loading the internal structure outward, hunting for a weak seam. Then a pressurized bulkhead collapsed deep inside the wreck. In the moments that followed, the artificial buoyancy was lost. The wreck sank again, and the hull ended up turned turtle, settling deeper than before. The massive steel island that had dominated the bay was gone. The sheer momentum of the heavy rotation displaced massive volumes of water, creating violent surface turbulence that rocked the surrounding salvage vessels. When the water finally cleared, the geometry of the job had inverted with the hull. The stable, dry working surface was gone, and the wreck's highest line was now its keel. Staging platforms were smashed and dragged under, and the sealed access points and air routes that had taken so long to build were suddenly useless, buried beneath the inverted mass. In a matter of seconds, the operation was forced into a total reset. It took an exhausting sequence of heavy lifting operations to finally shatter the unrelenting grip holding the dead warship on the ocean floor. The physical reality of the salvage site was entirely transformed. The vessel was completely upside down, presenting a long, flat expanse of heavy bottom steel just beneath the waves. To get air back inside an upside-down hull, the engineers had to build a new pneumatic path. Deep, vertical shafts driven straight down through the upturned bottom plating. Salvage divers and topside cutting teams mounted the keel. They used heavy underwater torches to burn wide access holes straight down through the thick steel floor plates of the warship. Long, cylindrical steel airlocks were hoisted over the water and bolted vertically onto these new openings. These metal tubes created rigid, watertight mechanical tunnels leading straight down into the pitch-black, flooded lower compartments of the inverted ship. Workers climbed down inside these vertical steel pipes, securing heavy patches from the inside and systematically closing off any remaining shattered pipeways or ruined vents. Once the new deep structural seals were heavily secured, the massive surface compressors were fired. They hammered heavy volumes of compressed air straight down through the vertical airlocks, injecting immense pneumatic force into the highest interior sections of the overturned hull. The internal gas pressure slowly gathered, pushing outward against the cold steel and downward against the heavy internal water. But the colossal suction of the dense ocean mud holding the superstructure was unyielding. The sheer physical friction of the buried steel binding against the heavy earth acted like a massive hydraulic anchor. The heavy lifting process became a brutal war of attrition. The topside engineers drove air down until the hull groaned and shuddered in the mud and the wreck clawed upward by a few hard inches. Then the trapped gas found a weakness, vented in a violent eruption of white water, and the mass dropped straight back into the seabed. Crews reset through the vertical airlocks, located the fresh rupture, welded on new patches, and fired the compressors again. The cycle repeated: lift, vent, drop, repair, each failure exposing the next weak point in the iron skin. 39 lifts stalled or ended in the sudden loss of trapped pressure. On the 40th, on November 2nd, 1928, the internal gas pressure finally overcame the deep mud's absolute grip. The heavy suction catastrophically broke. The massive 25,000-ton steel hull suddenly tore completely free from the ocean floor. She shot violently upward, breaking the rough surface in a massive, chaotic eruption of heavy displaced seawater and rapidly expanding air. The battlecruiser was successfully refloated, but she rode the surface entirely upside down. The long, flat bottom keel remained pointed permanently at the sky, while her ruined, heavy upper superstructure hung completely submerged in the dark water below. The massive deadweight target was finally torn from the mud and floating freely on the surface. but attempting to maneuver a fully inverted 25,000-ton warship across the open, unpredictable ocean presented one final, highly dangerous mechanical hazard. At Scapa Flow, the recovered giants were often not righted before the tow. The salvage engineers looking at the massive inverted steel island floating before them made a hard operational decision. They abandoned any attempt to roll the hull upright on the spot. The colossal battlecruiser would be towed exactly as she floated, entirely upside down. The physical reality of the recovered ship presented a massive navigational hazard. The vessel was a 25,000-ton deadweight mass floating purely on trapped internal displacement. Its long, flat keel was pointed permanently at the cold sky. The entire heavy upper architecture, including the massive armored bridge, the thick, vertical exhaust funnels, and the heavy main gun turrets, hung directly downward into the deep, dark water below. This inverted geometry created an immense and highly dangerous draft beneath the surface. A normally oriented ship is engineered to slice efficiently through the oncoming waves, but this blunt, metal object would fight the heavy ocean current every single foot of the way. The severe underwater drag created by the submerged massive superstructure made the floating wreckage incredibly unwieldy and highly unstable in heavy open swells. The towing vessels would have to drag a heavy, irregular shape through unpredictable open water. Righting the hull in open water would have demanded a staggering rig of leverage cables, massive counterweights, and a rare spell of perfect calm. A sudden shift in the wreck's center of gravity could have expelled the trapped air that was keeping the iron floating. One loss of buoyancy would have sent years of labor straight back to the ocean floor. With that risk unacceptable, the engineers accepted the dangers of an inverted transit to the mainland. Heavy maritime towing vessels surrounded the floating iron mountain. Thick steel towing cables were hauled out over the water and heavily shackled directly to the flat, rusted bottom plates of the upturned ship. The long and grueling journey across the sea commenced. Moving a massive, uncooperative steel block across miles of open ocean demanded continuous cable tension and careful surface navigation. The heavy surface tug strained fiercely against the immense underwater resistance of the submerged battlecruiser. The transit was agonizingly slow and vulnerable to weather and sea state. The massive metal structure rode low in the swells, making a bizarre and enormous target moving steadily toward its final destination. It was a massive 25,000-ton imperial warship navigating slowly toward the mainland with its bottom exposed to the open air. The final destination for the dead vessel was the heavy naval breaking yard at Rosyth. When the massive inverted hull finally arrived in the shallow harbor, it was carefully maneuvered into the tight physical confines of the heavy industrial docks. This successful harbor arrival marked the absolute end of the aggressive maritime heavy lift operation. The deep ocean had completely lost its tight grip on the immense metal prize. The maritime salvage crews stepped back and the heavy mainland demolition teams immediately took control of the dead hull. Hundreds of yard workers armed with industrial cutting torches swarmed the upside-down hull. They dismantled the ship plate by plate, cutting the armor that had survived combat, deliberate scuttling, mud suction, and catastrophic structural failure down into manageable scrap. Shore cranes hoisted the blocks away to be melted down. Within a short time, the battlecruiser was gone, erased into reclaimed steel, and the salvage campaign ended in demolition.